Hello, my name is Nathan Schauer, and I will be presenting work on simulation of wave propagation in fluid field fractures within a GFEM framework, which is part of my recently completed PhD at the University of Illinois. Guided waves that propagate along fluid field fractures are commonly called Krauklis waves. These are waves known to have phase velocity that approaches zero as frequency approaches zero, and to be highly dispersive. They have applications in numerous fields where the fractures cannot be directly assessed, as in magma field fractures near volcanoes, or for the oil industry to assess the ultimate geometry of a hydraulic fracture treatment. This figure exemplifies the multiphysicus phenomena, where on the left, there are waves in the elastic solid that are excited by the opening of this fracture, which in turn is directly related to the pressure in the fluid. There's a pressure wave propagating through this fracture. In this work, we propose a 3D GFEM methodology to simulate these Krauklis waves. In the outline, I will talk quickly about GFEM for fractures, the governing equations and solution method, comparison with analytical results and experiments, and lastly, a more complicated example. Starting with the GFEM for fractures, this equation represents the approximation of the displacement vector U. And it's comprised of a first term. There's just a standard FEM approximation, degrees of freedom A and shape functions phi, and a GFEM enriched approximation, where there are enrichment functions E. So a GFEM shape function is defined as the enrichment function times a standard FEM approximation to give local support. This is illustrated in this figure on the left, where there's FEM shape function times this enrichment function that gives rise to the GFEM shape function in the bottom. And this allows for the construction of shape functions that incorporate a priori knowledge about the solution. For instance, the Heaviside function here that can be used to model the jump in displacement in a fracture. Then the GFEM approximation space, just for the enrichments, is comprised of three terms: a polynomial enrichment to increase the accuracy, a discontinuous enrichment for elements that are completely cut by the fracture, and singular enrichments that can model partial opening of an element and also increases their accuracy by introducing the known square root of R singularity to the approximation space. The governing equations for this problem are the following. The solid is modeled with an elastic wave equation shown here, and the fluid with a compressible Navier-Stokes description with averaging. And the coupling between these two equations is through the pressure, that the pressure in the fluid is applied as attraction in the surfaces of the fracture, and the opening of the fracture, W, that is the jump in the displacement, that is solution of this elastic wave equations times the normal. After time discretization and spatial discretization, the system can be depicted like this, where U, P, and V are degrees of freedom of displacement, pressure, and velocity respectively. The terms of this matrix are shown here, and I'm not going to go through all of them due to time constraints, but we'll answer any questions on them after this presentation. I also want to point that this system is symmetric and is also linear. So if the time step does not change, it can be assembled and factorized only once. Starting with a comparison with analytical solutions by Lipovsky and Dunham. The example we consider has thickness of 0.1 meter and rollers in both sides to mimic plane strain conditions. The domain is made big enough to avoid boundary effects. And in the middle, there's a fracture. Here in red is the fluid field FEM mesh. This fracture has 1 meter. The material properties are shown here on the bottom right. And the boundary conditions for this fracture are zero normal velocity in this blue boundary. And the only thing that excites the system is in this red boundary here, and it's a pressure pulse. So this pressure pulse is going to propagate back and forth in this fracture. This is a video that will show the the waves in the solid here on the left through the stress in the x-axis direction, the opening of the fracture in this part, and the pressure in the fluid. And these two are closely related. I'll play the video now. The waves again can be seen in the solid, and the pressure and the opening are closely related. And for this problem, the phase velocity with respect to frequency can be calculated. These were calculated for 4 different openings, initial openings, 10 millimeters, 3, 1.5 millimeter. And we're compared with analytical solutions. The GFEM solution is in hollow markers, while the analytical solutions are in solid lines, and a great match for all 4 different initial openings can be seen. Next, I'll show some comparisons with experiments that were conducted by Kenneth Desmond in the New Jersey facility of ExxonMobil. A simplified setup of the experiment is shown here on the left, where there's a rectangular domain in green and an embedded fracture in red. There are 3 experiments with the different dimensions that are shown in this table here, and the material properties are shown in the bottom right. For this problem also, the phase velocity with respect to frequency was calculated, and the results are showing here for the 3 experiments. Experiment 1 in blue, 2 in orange, and 3 in green. And in markers are the experiments, post-process variables, and in solid lines, the solutions with the GFEM. And a great agreement can be seen for most of the part of those frequencies. Also, 2D analytical solutions are shown in dashed line here, which exemplify that even for this rectangular fracture, 3D effects are important and need to be considered for accurate simulations. Lastly, I will show a 3D elliptical fracture, and the domain is shown here on the left, where there's an embedded elliptical fracture. This fracture is 0.5 meter by 1 meter. This is the same length as the first example shown in this presentation, and this is used to compare both examples later. Also, the connection where the pressure wave is applied is a smaller region, is just part of this left boundary of the ellipse. And this is a more realistic connection with the size of a wellbore. And these are the material properties, which are the same as the material properties in the first example. This is a video of the time evolution of fluid pressure on the fracture. The boundary conditions are in blue, 0 normal velocity, and in red, a pressure pulse that is going to be applied in a short amount of time and then will propagate through the domain. I'll play the video now. And I'll stop just a little bit here to emphasize that even though the maximum excitation here at this boundary was 0.7, at the tip, higher pressures can be achieved due to resonance of this fracture and its geometry. I'll continue the video now, and very smooth solutions, stable solutions can be seen for the pressure in this fluid field fracture. Next, the resonant frequencies of this fracture are compared between the plane strain fracture here in blue and the elliptical fracture in red. And these are compared to the fracture transfer function, which is a way to measure the resonance modes of these fractures, and is defined by the division of the Fourier transform of the average velocity at the mouth divided by the Fourier transform of the pressure at the mouth of these fractures. And it can be seen that very different resonant frequencies can be achieved. And this is a very important information because it can be used to assess the geometry of those fractures. And in conclusion, I tried to show here a fully 3D methodology to simulate waves in fluid field fractures, which has been verified and validated. Shown that 3D effects can be important even for rectangular fractures, as in the experiments, the comparison with experiments. And the method allows for the analysis of more realistic geometries and boundary conditions, like the elliptical fracture that I shown in the last example. And I would like to point out that the GFEM is ideal for inverse problems, and because there's no need to fit the mesh to the fracture. So in inverse problems, where you want to try different fracture geometries to see the one that fits the field data, you don't need to create different meshes for the different fracture geometries with the GFEM. With that, I would like to acknowledge and thank our sponsors, and I'll be glad to talk to you and answer questions after this presentation. Thank you very much for your time and attention.